Welcome to all. Today we can discuss something about shafting. A shaft is a rotating machine element which is used to transmit power from one place to another. The power is delivered to the shaft by some tangential force, and the resultant torque set up within the shaft permits the power to be transferred to various machines linked up to the shaft. In order to transfer the power from one shaft to another, the various members such as pulleys, gears, etc. are mounted on it. Actually, a shaft is a rotating machine element which is used to transmit power from one place to another. The power is delivered to the shaft by some tangential forces, and the resultant torque or twisting moment set up within the shaft permits the power to be transferred to various machines linked up to the shaft. That is the condition. Materials used for shafts. The materials used for shafts should have the following properties. First one, it should have high strength. The material using for the construction of shaft must have high strength. It should have good machinability. It should have low notch sensitivity factor. It should have good heat treatment properties. It should have good heat treatment properties. And finally, it should have high wear resistant properties. And when we comes to the design of shaft, the shaft may be designed based on strength or based on rigidity and stiffness. In the designing shaft based on strength, in the designing shafts based on strength, the following cases may be considered. These are the different conditions. First one, shafts subjected to twisting moment only or torque only. Next, shafts subjected to bending moment only. Next, shafts subjected to combined twisting and bending moment. Here both the twisting moment, torque and bending moment, both are acting on the shaft simultaneously. Finally, shafts subjected to axial loads in addition to combined torsional and bending loads. In addition to this torsional and bending loads, in the fourth case, shafts are subjected by axial loads also. First case, shafts subjected to twisting moment. Here we know that this equation is already, we know T by J is equal to tau by R, where T is equal to torque, J is equal to polar moment of inertia, tau is equal to torsional shear stress, and R is the distance of the outermost layer from the neutral axis. R is equal to distance from the neutral axis to the outermost fiber. That is equal to d by 2, where d is the diameter of the shaft. We have already know that J is equal to polar moment of inertia is equal to pi by 32 into d raised to 4, pi d raised to 4 by 32. Then the equation may be rewritten as T by J, T divided by pi d raised to 4 by 32 is equal to tau by R, tau divided by d by 2. Then T is equal to pi by 16 into d cube into tau, pi by 16 tau d cube. This is one important equation. This is an important equation. Torque or twisting moment is equal to pi d cube by 16 tau. Then when the given shaft is a hollow shaft having outer diameter dO and inner diameter di, then this polar moment of inertia is equal to J is equal to pi by 32 into dO raised to 4 minus di raised to 4. This is the polar moment of inertia of a hollow shaft. Here dO and di outside and inside diameter of the shaft, and we can treat this r as r is equal to dO by 2. R is equal to distance from the neutral axis to the outermost fiber, that's equal to dO by 2. Then we can substitute these values in the equation. T by J is equal to tau by R. Then we will get this particular equation. Then from this equation we can write T is equal to pi by 16 into tau into dO raised to 4 minus di raised to 4 divided by dO. Then we introduce another term k, that k is equal to ratio of inside diameter and outside diameter of the shaft, that's equal to di by dO. Then the equation 3 may be rewritten as pi by 16 into tau into dO raised to 4 by dO into 1 minus di by dO whole raised to 4. Then we can substitute di by dO as k. Then T, twisting moment, is equal to pi by 16 into tau into dO cube into 1 minus k raised to 4. This is another important equation. Equation number 4. These two equations are most important equations while we considering the design of the shaft subjected to twisting moment only. Then from the equations 3 or 4, the outside and inside diameter of a hollow shaft may be determined by using this equation 3 or 4. We can determine the outside and inside diameter of the hollow shaft. These are the secondary conditions. We can discuss this in detail. The hollow shafts are usually used in marine work. Then when a hollow shaft is to be made equal in strength to a solid shaft, the twisting moment of both shafts must be same. When a hollow shaft is to be made equal in strength to a solid shaft having diameter d. Solid shaft having diameter d and a hollow shaft having diameters dO and di, outside and inside diameters dO and di respectively. Then T is equal to pi by 16 into tau into dO raised to 4 minus di raised to 4 divided by dO. This is the twisting moment of hollow shaft that must be equal to twisting moment of the solid shaft having diameter d. Then we can say that dO raised to 4 minus di raised to 4 divided by dO must be equal to d cube, or dO cube. We can take dO outside this particular terms, then dO cube into 1 minus k raised to 4, that must be equal to d cube. This is another condition. Then the twisting moment T may be obtained by using the following relation. Here power transmitted by the shaft is equal to P is equal to 2 pi nt by 60. Then we can obtain the equation for torque is equal to P into 60 divided by 2 pi n, where n is the RPM, speed of the shaft in RPM. And in the case of belt drives, twisting moment is equal to T1 minus T2 into R. In the case of belt drives, here this is the tension in the tight side T1, this is the tension in the slack side T2. In the case of belt drives, the twisting moment T is given by T is equal to T1 minus T2 into R, and While referring this particular figure, this is the pulley. This is the pulley. Pulley is subjected by a tension in this direction or in this side, that's equal to T1. This T1 is the tension in the tight side, and in the another side having a tension, that tension is represented by T2, that is the tension in the slack side. Then this, due to this T1, this pulley is having a tendency to rotate in the anti-clockwise direction, and due to this T2, this pulley having a tendency to rotate in the clockwise direction. Then that this twisting moment is equal to T1 into R, this twisting moment is equal to T2 into R, then the overall twisting moment, that T is equal to T1 minus T2 into R, where R is the radius of the pulley. T1 and T2 is equal to tensions in the tight side and slack side of the belt respectively. And here is the first question. Find the diameter of a solid shaft to transmit 20 kilowatt at 200 rpm. Here this power transmitted is equal to 20 kilowatt, and N is equal to 200 rpm given in the question, 200 rpm. The ultimate shear stress for the steel may be taken as 360 megapascal, and the factor of safety is equal to 8. Here ultimate shear stress, tau ultimate is equal to 360 megapascal, and factor of safety is equal to 8. If the hollow shaft is to be used in the place of solid shaft, find the inside and outside diameter when the ratio of the inside to outside diameter is equal to 0.5. Inside to outside, di divided by do is equal to 0.5 in the case of hollow shaft. Find the diameter of the solid shaft, that is a question. Then di by do is equal to 0.5, P is equal to 20 kilowatt, that is equal to 20 into 10 raised to 3 watts. Tau u is equal to 360 megapascal, factor of safety is equal to 8. Then the allowable shear stress is equal to tau, that's equal to tau u by factor of safety, that's equal to 45 Newton per mm square. Then diameter of the solid shaft, we can calculate the torque transmitted, that's equal to P into 60 by 2 pi n. We have already discussed this equation. Then 20 into 10 raised to 3 into 60 divided by 2 pi into n, where n is the RPM of the shaft. Then we can easily calculate this torque transmitted, that is equal to 955, that's equal to 955 into 10 raised to 3 Newton mm. Then we also know that torque transmitted by the solid shaft, that T is equal to pi by 16 into tau into d cube. We have already discussed this equation. Then from equating these two values, we can easily calculate this d cube. Then we can calculate the diameter of the solid shaft, that d is equal to 47.6, say 50 m. We can round up this value to 50 m. Then instead of solid shaft, we can use a hollow shaft. Then we can find out the diameters of the hollow shaft. di is equal to inside diameter, do is equal to outside diameter. Then torque transmitted is equal to pi by 16 into tau into do cube into 1 minus k raised to 4. 1 minus k raised to 4. Here k is equal to 0.5. Then substituting all the values here in this particular equation, we can calculate do. do is equal to 48.6 or 50 mm. Then di is equal to 0.5 do, that's equal to 25 mm. We can round up this value, 48.6 into 50 mm. That is the final answer. Thank you all.